All right. Well, hello class, and welcome to the first recorded lecture in our course on spacecraft dynamics and control, otherwise known as orbital mechanics and some other things. So I'm your instructor, Matthew Pete. So in today's first recorded lecture, we're going to be talking about, well, a few things. In the first part A, I suppose, will be just introducing organizational class material. Nothing particularly exciting or fancy. I'll just introduce myself and the structure of the class and what's going to be in it. And after that, we'll begin talking about sort of the history of orbital mechanics, starting from the Greeks, going through the scientific revolution, the Enlightenment, and more or less ending up with Newton, who comes out slightly after Kepler. But before we get there, let me introduce the class. So this is the first lecture. And let me start by introducing myself somewhat, at least in the recorded part. So who am I? I'm Matt Pete. So what's my background? So I have studied aerospace engineering, in particular orbital mechanics, in some depth. I've taught this class, 462 at Arizona State, and orbital mechanics in general before that. I've forgotten the number of times I've taught it, quite a few times. At Arizona State here, I think I'm the only person who teaches orbital mechanics. So if anyone's taken orbital mechanics before at Arizona State, they've taken it from me. If you need to retake it next semester or next year, I'll be teaching it again. And this is a perk of the job. I would say orbital mechanics is my favorite class. Significantly, I also teach a graduate class in control systems. But I think orbital mechanics is the most interesting. I think it's generally the most interesting for students as well. A lot of you, most of you who are taking this class are in the astro track of aerospace and astronautical engineering. And for many of you, right, learning about space and space exploration is why you came into the field. I think it's certainly why I came into the field, and the privilege of actually teaching this class on a regular basis is, well, it's not something I value lightly. That said, okay, you'll find this class entertaining. I certainly do. I try and make it as entertaining as possible while also cramming a lot of material in there, so there's no shortage of material. Here at Arizona State, this is probably the only orbits class you'll ever take, because I don't think we have a graduate one. If we did, I would probably be teaching it, but we don't. So I try and put essentially probably too much material into this class, honestly, maybe two courses worth. But I think the material is so interesting that you'll engage with it well enough that you'll be able to digest it all. And if not, you just watch the lecture twice because they're recorded right now, and then maybe you'll get it the second time. Come back to it later. So what's my background? So I've been in orbits and aerospace engineering and space-related applications for quite some time. So I'm originally from North Carolina. Stayed on the East Coast. Probably heard of it at some point. From there, I went to the University of Texas at Austin. That's me right here, UT Austin, where I majored in aerospace engineering. I seem to find some spare time on my hands, so I took a few extra courses, and one thing led to another. And in the end, I took enough extra courses that I got a second degree in physics. Because physics and space, right? They're kind of related, so that's why I got into it. I took some celestial mechanics courses there as well. Didn't do too well in those because they were graduate. I took a lot of graduate level courses at UT Austin. In the orbits ones, I did well, and the celestial mechanics not so well. But forget about that. From there, I went to Stanford University in the Aeronautics and Astronautics program. Also took all the orbits classes there, a lot of great ones. So I don't know how many I've taken orbit mechanical classes I've taken in my life, but I would say it's around over 10. Quite a few. So you're taking one, which is fine, but if you get a chance to take any graduate courses, there are great graduate courses in orbital mechanics at some of the big orbit schools, Colorado, Austin, Stanford has, well, they used to have quite a few. I'm not sure what their situation is now. Urbana-Champaign, I think they still have quite a few, although some of their older professors are stepping down. In particular, the guys who wrote the textbook for this class, Pressing and Conway, are from Urbana-Champaign. So, but I think they're both retired now. So I don't know the status of their orbits classes at this moment in time. After Stanford, I worked briefly at NASA JSC in Clear Lake, Texas, near Houston, which is not the best place to live if you're choosing a place based on climate. Lots of humidity, lots of mosquitoes, not great. But, Johnson Space Center is there, so, that's a lot of space applications. You may end up living there if you go into space as sort of a career choice. So briefly there, about a year, moved on to Stanford, master's program. Was briefly involved for about a year in both the Gravity Probe B projects and the Supernova Accelerator project. This one was actually over at Lawrence Berkeley National Lab, so I have to commute. I don't know, God, how long was it? It's like it was a pretty long commute over from Stanford to Berkeley. It was about an hour. Just the other side of the bay, but a lot of traffic. After I finished my graduate studies, I went to Institut National pour la Recherche en Informatique et en Automatique and actually Versailles, which technically Les Chenets, but right outside Versailles, which is near Paris, right? I have lots of funding, including career awards, yada, yada, yada. Here's my office. This semester, I'm not going to be in it very much. But so most of the office hours will be through Zoom. Our lab is in the Goldwater Center, which is where if you're attending this class in person, there are, I think, a few of you, then it's the building right next door. So I have a lab over there. My contributions, right, to research, what my interests are, just sort of to let you know a little bit about myself. My contributions are mainly in the area of control theory. So if you go to my website, here's my website. It says control.asu, sort of gives you an implication that maybe I do controls. But you go over there, right? You can go and browse some of my publications. I made some interesting contributions here. You may be interested here, for example, I have a paper on space elevators, so orbital mechanics. I have a paper on orbital mechanics, so I have some research interests in this area as well. So you can go through it, and it's fairly long, but I think it's a little bit entertaining. I sometimes say research shouldn't be boring, even if it is controls and orbital mechanics. Well, orbital mechanics is never boring, but controls sometimes can seem boring. But if you try and make it exciting by having new ideas and telling new stories and things like that. But this paper, I think you might find interesting if you decided to take a read into research in orbits. Other than that, right, you can browse the website. In particular, if you go to under classes taught, we'll find this course, Orbital Mechanics here, with the notes, the lecture notes that I'll be using throughout the course. You can just click on them and download them. At the moment, they're a little bit out of date, so I apologize for that. I'll be updating them shortly, but not today. So obviously, I use lecture slides. Please don't refer to them as PowerPoints in class or in discussion, because they're not made with PowerPoint, they're made with LaTeX. And in fact, I don't actually use any Microsoft products whatsoever except for Windows, which seems to be what everyone uses, so I can't really get out of it. But I don't use PowerPoint to create these, I use LaTeX, so please don't make that mistake. It's very insulting for those of us who pride ourselves on not using Microsoft products, because I'm not sure I can articulate exactly why I don't use Microsoft products, but I don't, so don't accuse me of that. So the research projects, the publication list you just saw, software related to my research, some other classes I teach here. I'll post. I don't think I currently have a link to the YouTube site here on the classes taught, but that's where I'll be posting these lectures on YouTube. Some of the students in my research group, currently Brendan, Morgan, Sachin, Alexander, and Amritam. Of course, that'll change over time. Some my sponsored research from funding, mainly from NSF. I don't get any funding from NASA at the moment. If NASA's watching, please fund me. No, but seriously, most of my funding is from NSF. Let's see. Zoom back in. So my expertise is obviously a research paper on orbits, but my main research is in controls. Perhaps my earliest contributions were in the area of delayed systems. So that's control when there's a significant delay between when you send out the control signal and when you receive feedback. So control is always through feedback. So if there's a delay in the system, that causes all sorts of problems. Delayed systems sort of involve transport of information, and really the simplest form of what's a more general class of system called PDE systems, or partial differential equation systems. So PDEs actually date back to the time of Newton, as do all differential equations. So partial differential equations, just differential equations in general, all date from that same time. It's just that ordinary differential equations we know how to control very, very well. But PDE systems, because of their nature, they're sort of governed by boundary conditions and things like that, are much harder to control, and so there's a lot of research going into control of partial differential equations. So my main contribution in that area has been to sort of reformulate partial differential equations into something called partial integral equations, which are more amenable to scientific computation systems, such as semi-definite programming and so forth. I've also contributed quite a bit to the theory of nonlinear systems, so Lyapunov theory, converse Lyapunov theory, regions of attraction, that kind of thing. All of these research topics are interlinked with theory of computation. In particular, scientific computing, I don't mean simulation, I mean optimization. So when we're controlling things, we're optimizing something. So control problems are just special cases of optimization problems. So our lab also considers optimization per se, right, by itself. So algorithms for optimization. And then, of course, machine learning is a special case of optimization. You may have heard of machine learning more than you've heard of sort of control or general forms of optimization, but machine learning is just function fitting. In fact, actually, the first machine learning algorithm can be attributed to Carl Friedrich Gauss, which is what you probably know as least squares. So obviously, the algorithms we have for machine learning have improved over time, but basically machine learning is still just function fitting, which is posed as an optimization problem. So we have some interesting advances in machine learning, finding new ways to parameterize functions to fit through kernel functions. So if you are interested in machine learning, you can browse my website and find some of those papers there. All of these sort of fundamental theoretical contributions are with an eye towards applications. And in particular, the applications that most interest me are well, what I was most interested in early, and still mostly interested in, is control of nuclear fusion. So you may be familiar with fission, nuclear fission reactors. That's what we have now, where you have U-235, right? And you hit it with a neutron, and it breaks into constituent particles and releases lots of energy, gamma rays. Fusion is sort of the opposite. You take constituent particles, typical hydrogen or deuterium, to make them a little bit heavier, have more inertia. So hydrogen and deuterium. You give them enough kinetic energy. Well, how much kinetic energy do you need? Well, typically about 10 million degrees Kelvin. Oops. That's hot, by the way. If you give them enough kinetic energy, then these particles, they ionize first of all, and then they have a positive charge on both of them. Right? This is deuterium. This is hydrogen. And naturally, right, when they get close to each other, they repel because they have like charges here. Right? So these like charges repel. And so normally hydrogen, you put hydrogen in a balloon, it doesn't turn into a nuclear fusion reaction, hopefully. But if you were to heat that balloon up to 10 million degrees Kelvin, wow, pow, that would pop. It would pop in the sense that it would form a nuclear fusion reaction. Fortunately, balloons typically don't, well, actually balloons are mostly helium. Helium also, but you have to get it higher than 10 million degrees Kelvin because it's got 2 charged particles in there. Anyway, you got to get up to 10 million degrees Kelvin. Hydrogen is more in like blimps and stuff like that. But you get up to 10 million degrees Kelvin, and there's enough inertia in these particles just through kinetic energy that they're able to get close enough so that the strong nuclear force takes over. It overwhelms the positive electrostatic repulsion and fuses those atoms together and produces lots of energy. Right. So the problem, of course, is that there's no balloons or blimps or anything else or any material known to man that can withstand 10 million degrees Kelvin. For reference, 10 million degrees Kelvin is about approximately the temperature at the core of the sun. That's my sun. Okay, then how do we do it? How do we create? Well, basically we don't. This is why we don't have fusion reactions, because 10 million degrees we can't control the plasma. We can't make it stay in one spot. In tokamaks, however, we have at least an approximate solution, which is you put these charged particles in a uniform magnetic field. Right? So there's a magnetic field, and then when they try and escape, right, these charged particles, they start going that way. Well, if you use the right-hand rule, Faraday's law, or no, wait, it's Gauss's law, right? Gauss. Yeah, Gauss worked with Weber, and he discovered lots of things, right? Yeah, we'll talk about Gauss later. Anyway, so right-hand rule, charge going that way, magnetic field going that way, resulting force going the third way, right? So this causes the particles to oscillate and not escape, stay in the magnetic field. The trick is, however, they can still move along the field lines, and so somehow you've got to reconnect the field lines, like that. So that's what tokamaks do. They have these big magnets here, which bend the magnetic field back on itself. Magnetism doesn't work quite like that because you can't really bend them back on themselves. And in particular, the field here is weaker than it is in here, and so you get some issues. And so they have another field called the poloidal field, which is actually caused by the motion of the particles themselves, which cause the magnetic field to oscillate. It looks like a cruller. That's a kind of donut. If you ever seen a cruller, it's like sort of a torus shape. I don't know. I can't draw a cruller. Sorry. In any case, this is sort of open loop control, right? There's no active control in here, and it tends to be that motions, perturbations to the plasma, that is the ionized particles, creates their own little magnetic fields, which destabilizes the main magnetic field, and so that's why we don't have fusion reactions, because like when you get these things hot enough, those perturbations become unstable, and then the whole field deteriorates. You lose confinement, and then you've created a $10 billion tokamak reactor, which now has been burnt to a crisp. ITER, by the way, is under construction in Cadarache, France, for that purpose. And so the idea is then you want to use control to stabilize this magnetic field, try and prevent it from deteriorating and losing confinement. So it's obviously a big application of PDEs, right, because these are spatially distributed quantities, both the plasma and the magnetic field. I also have some less sort of obvious interests in research, so particularly immunology. My interest in research in immunology actually predates this whole immunotherapy thing, which you may have heard of now as a treatment for cancer. But basically the idea is our immune system, and here actually I should erase a bunch of junk. Right. So the thing is, here's you, right? This is you. Maybe you look like a robot. Sorry about that. But you get exposed to viruses, say COVID-19. Let's see, which starts doing a little exponential growth in your body. So that's bad, right? Exponential growth is generally bad. So what happens is that your body, first it senses that exponential growth. So there's a sensor, which is through things called dendritic cells. We typically think of those as the sensors. They sweep up, sort of do a survey of what's going on in the body, take that information to the lymph nodes, not lymph nodes, which try and figure out what's going on. They look at these rates of change and stuff, and based on whether they think this is a threat or not, they will signal a larger immune reaction through helper and regulatory cells. So if they think it's harmless, they'll try and create dynamics that increase your regulatory response, and if they think it's harmful, they'll increase the helper response. And then you have actuators here in the form of CD8s, killer T cells, that kind of thing. All right, so it's a feedback loop, and the controls part of it, of course, is what's going on in the lymph node. So modeling that control system, right, and then fixing it in the case of, say, cancer. In the case, well, we don't work too much with COVID-19. But in the case of cancer, in the case of allergies, autoimmunity, that kind of thing, what goes wrong with that control system, understanding what goes wrong with the control system, of course, is the first step in fixing it. So moving your immune state to something where you can you have a healthy response to that particular disease, cancer, autoimmunity, allergies, what have you. Okay. So it's really a controls problem, and it's a sort of a very nonlinear system, something we've been looking at for quite some time, thinking of it how it works as a circuit, a biological circuit. We have some interest in SOIF robots, which actually is part of PDEs, so spatially distributed robots, and of course control in space. So optimal path planning is obviously a big optimal continuous thrust transfers and things like that is obviously a big application of control systems. More classical one is control of attitude. So if you have a spacecraft here and it has an observation dish, or maybe you have a space telescope, say the Kepler space telescope, right? Controlling those spacecraft is actually quite difficult. Unlike for aircraft, which the atmosphere allows us to sort of linearize the dynamics, and we'll talk about this at the end of the class in more detail. The dynamics in space are very nonlinear because, right, there's no atmosphere, nonlinear effects. Everything's nonlinear, but in the atmosphere, nonlinear effects are sort of damped out. But in space, we have no such luck. So the dynamics are very nonlinear, and so designing control systems for those is very important. Let's see, did I miss anything? Well, probably, but There's also like a connection between machine learning here, by the way, and immunology as well. I probably missed a few things. You can check my website if you're interested in any of my other research activities. But that just gives you a flavor of sort of like the kind of things that I like, right? The things that I think are cool, right? Sort of new ideas, space applications always. I mean, nuclear fusion, right? We'll talk about it when we talk about propulsion. Nuclear fusion is, of course, the key to also not just unlimited energy, right, which you need for space travel, but also there's things called magnetohydrodynamic propulsion as well, various forms of EM propulsion, which you need to stabilize a field in order to get that. It's not a fusion rocket, but it's a plasma rocket. So in any case, I should probably move on to slide 3, which actually covers the course as opposed to just myself. Although it's you know, I think it's important to like sort of humanize myself in the class, just to give you an idea of, you know, what we can talk about. If you want to chat with me about any of those topics, please come to my office hours, and I'd be happy to discuss any if you're interested in research, any of those topics. In any case. Now I'm going to briefly in the next in the next 3 slides talk about the overview of the course. So what are we going to cover? So the first entire half of the course is going to be essentially the two-body problem, elliptic orbits. So in the first lecture, this lecture, we'll be talking about the derivation of the model, right? How we got to elliptic orbits, right? Why it makes sense, sort of some of the history behind it, how actually, in fact, most of natural philosophy, or what we now refer to as science, was focused on these questions of how the planets move, up until, I suppose, the time of Newton, where it was more or less solved. So a lot of scientific developments and continuing scientific developments, even relativity, have been focused on explaining one particular problem, which is the two-body problem, which is these elliptic orbits. Okay. So in the first part of the class, we're going to be talking about those elliptic orbits, right? How to convert between position and velocity and the orbital elements, most of which are invariant. Position and velocity vary continuously with time. However, the orbital elements of a planet or a spacecraft, only the true anomaly changes. All the other orbital elements are constant. Of course, there's an exception to that, which is we'll talk about later, which is these perturbations due to drag and Earth oblateness and so forth. So we're going to spend a great deal of time talking about conversion between position and velocity in orbital elements, how to propagate orbital elements forward in time, how to solve Lambert's problem, which is basically a two-point problem, right? You have a point here and a point here, and find the orbit between those 2 points in a given delta t. That's Lambert. We'll talk about that later. We'll then talk about quite a bit about maneuvering, so the Hohmann transfer, the bielliptic transfer, various orbital maneuverings within the model of sort of delta V propulsion. So we'll talk about delta V propulsion later. Incidentally, that part of the class, that orbital maneuvering, factors a great deal in my paper on space elevator mechanics. And also, I should mention, we work a little bit with Peter Swan, who's International Space Elevator Consortium, who's here in Phoenix, and he should be coming in to talk to the class at some point, give a little guest lecture. We'll also talk about interplanetary mission planning, which is a little bit more complicated. Again, fits into the context of space elevators. Talk about gravity assist maneuvers, how those work, patched conic maneuvers. Really, interplanetary mission planning is a much more applied version of just what we've talked about before. Patch conics means everything is an ellipse. We reduce everything to a two-body problem. There's no three-body problems. So then we'll get to changes to that two-body problem, the earthobladeness, drag, atmospheric drag, that is, and so forth. And finally, I think Lambert also factors here under orbital estimation. Finally, in the second half of the class, we'll cover some other things, which we didn't cover in the first half of the class, and things that aren't purely orbital mechanics. So specifically, we talk about propulsion, how to create that delta V, right, for orbital maneuvering. We'll spend considerable time on attitude dynamics, so how to change your spacecraft orientation, right? Using what do you use in space? Because you don't have atmosphere, there's no control surfaces on there's no airplanes, right? There's no wings. So how do you create torque in space? I'll talk about the various forms of creating torque, right? And then we'll talk about Euler's equations and a little bit about control, perhaps, at the very end. So that's a summary of the class, what we're going to go through. We'll have a midterm about here before we start talking about propulsion. So when we get to the propulsion lecture, which is a bit of a level of lecture 12 or something like that, or maybe 13, that'll be post-midterm. So just FYI there. The structure of the class itself. So first of all, the class resources. So the textbook that we require is that one I mentioned earlier by Prussing and Conway. What to say about it? I have to be careful because I'm posting these things on the internet, so I hate doing that, because then I can't say things which are they're jokes, right? But they could be misinterpreted or something like that. So I can't say anything bad, but I guess I'll just risk it, and because this is sort of about 20 minutes into the lecture, so maybe no one will watch it. So first of all textbooks have shortcomings. Prussing and Conway is my favorite for this class. It's almost a little too advanced for undergraduate classes. It's almost a graduate text, but I don't think it is. I use it because A, it's short. The optional textbook for this class, Curtis, is ridiculously long for the amount of material it covers. And far too wordy. No one reads it. No student is going to read the entirety of Curtis. It's just not possible. Prussing and Conway, by contrast, gets to the point. It's not a complete substitute for these lectures. You have to watch the lectures, of course. But it follows the lectures very well, right? The material is organized similar to how I organize this course, which is a plus. So follows the lectures. Is short, relatively short. It's witty at times. It has a few jokes in there, and it's serious, right? It's a serious text. If you say you learned orbits from Prussing and Conway, people will take it a little more seriously, because it's a serious textbook, and it's a respectable textbook. Now, by contrast, orbital mechanics for engineering students, this is it's still a serious textbook. But, come on, right? Orbital mechanics for engineering students. Think about that title, right? What is that saying? Is there an orbital mechanics which is not for engineering students? Is this dumbed down or made sufficiently verbose or lengthy that engineering students can somehow handle it, or it's dense enough for engineering students? I find that a little bit, patronizing, right? Engineering students are the people who are going to use orbital mechanics. No one else uses orbital mechanics except engineering students. So I no, for engineering, the title itself, little bit off-putting, I find. The text itself is relatively comprehensive. It's a little bit, it has more examples. It has nice examples, lots of examples. It's got lots of problems. So some of the problems that we assign will be out of Curtis. So lots of problems, and maybe that's the student part, right? It's like the orbital mechanics by Pressing and Conway could be used by professionals. This is more geared for students. If they just got rid of engineering there for students, right? That'd be perfect, nice and clean. But anyway, it's got lots of problems, and we'll occasionally assign problems out of Curtis. If you don't have to have a copy of Curtis. In case you don't, I'll like re-explain the problems in the problem set. But if you can, it's not very expensive. That's a plus. It's much cheaper than Pressing and Conway. So if you can get a copy of Curtis, please do so. It's it's a good reference to have. That said, creating these lectures, I have Pressing and Conway on my desk. Curtis is in my office, and I haven't seen it for 8 months. Also, they don't send me desk copies, so that does not influence, however, my opinions on the subject. Also, I have no sponsorship or anything. I have no skin in the game. This is just my opinion on Pressing and Conway versus Curtis. Incidentally, there's lots of other textbooks which are probably too advanced for this course. Methods and Vallado is a fantastic orbital mechanics by Vallado is here. I should write that down. Vallado is an amazing text. I sometimes consider using it, but it's really too advanced. It has too much information for an undergraduate class. But look up Vallado if you feel like it. Also cheap. It's worth getting a copy. Okay, so those are the two basic textbooks. You need textbooks for any course, so those are the two. Some other interesting resources which I encourage you, but obviously they're not required. Resources, right, I can't say this without like sort of smiling, but the Kerbal Space Program, right, is probably the best best application of orbital mechanics, holistic application of this course that you're going to find. It's when I first linked this, it was like in beta. It's now developed, and they keep adding content. It's a great little program. You have your little Kerbals there, let's see if you can show something. Some nice tutorials on designing rockets, and then the mission planning using delta V's, right? So I encourage you to take a look if you feel so motivated to construct your own Kerbal Space Program. And get maybe even if you want to do a project in this course, right? You could design a pretty cool Kerbal Space launch program to get to say if you wanted to do a gravity assist or something like that. Kerbal Space Program, that would be, I haven't seen any online, so that would be cool. All right, so okay, without plugging Kerbal Space Program anymore, go back to my lecture notes. Oops, too far. Not far enough. Okay. Next, also, if you want to look at these elliptic orbits in sort of a pretty format, Universe Sandbox is a nice application for sort of spitballing how these planets move, and of course you can add meteorites or spaceships as well in there. In fact, actually, some of the demos that I'll show in this course come from the Universe Sandbox, so that's also nice. And lastly, and perhaps the one I would encourage you most, maybe Kerbal Space Program as well, on is one of these apps for your iPhone. There are several of them, astronomy apps. Sky Safari is probably the best. So what this allows you to do, and I've got I've got Sky Safari here somewhere. I have various versions of Sky Safari. I'm not sure which is the most recent. Yeah. So what it does is it allows you to identify various things that we talk about in this course. In particular, okay, so there's Sky Safari 5 I have. Okay. Right. So let's see. Particularly if you activate right there the compass. I don't know if you can see this. If I get it close enough, will you be able to see it? Yeah, there you go. Sort of. Okay, so maybe I need to turn off my background, which I'm not going to do. Right, so if I put it in front of me. Oh, yeah, there we go. Okay. Yeah, so there we go. Learning how to do this on the line. So it actually syncs to your GPS and your compass. And allows you to look around in the sky and see the various things that we're talking about. So it's particularly the ecliptic. If you want to find any of the planets, you just do a search for the planet and look around till you find it. See, there's the moon. Let's see if we can find any of the planets. So the sun, you can tell what time it is when the sun's coming up. Unfortunately, I'm doing this near the conjunction of Jupiter and Saturn, and Venus is also close to the sun, so none of the planets are in the sky tonight. So you can see where they are. They're like down there, right? You can find they're below the floor. I can locate them. They're like over there, right, just below the horizon. Actually, they should be coming up fairly soon because it's late. So yeah, unfortunately, all the planets are over there, so you can't see them. But you can easily identify where all of these things are and sort of relate them. This is nice because in this modern day and age, right, there's Mars over there, by the way. In this modern day and age, you can't look up in the sky and see stars anymore, right? It's a bummer, but there's so much light pollution, there's so much regular pollution that you look up and you see a few stars, but you can't see lots of stars. And it's really hard to identify which are the planets and which aren't. And so if you want to see the sort of a simulated version of what the sky looked like, when people were developing these models, there's the Hubble Space Telescope, by the way. You can download the app and sort of have an artificial reality version of the night sky. So I do encourage you to like demo that or whatever. It's not required, of course. Just I like it. Also, if you have a telescope, it makes life incredibly easier. I do have a telescope, by the way, a Dobson reflector, FYI, just so you know a little bit more about me. The structure of the course, beyond this introductory material, I'll probably wrap up about now. So the structure of the course, all of these notes, all of the assignments will be through Blackboard. The midterms and such will be virtual, online. The format of the class, and I'll talk about this more because it's not really relevant for this part of the lecture. The format of the class will be disputation. So I'm a big fan of the scholastic methods of teaching, which probably dates me to about 600 BC or AD, where the lectures are separate, or you sort of give a lecture, and then you have a disputation. So the students do the disputation, supervised by the instructor, sort of applying what they learned in the lecture to make arguments for or against a thesis. Right. So disputation was from the time of Plato until the time of Galileo, really. Galileo, most of his works are in disputation format. Most of the teaching was in disputation format up until that time. So this class, I think, like this, the whole recorded lecture thing is a boon because it allows us to separate out these recorded lectures, this sort of inefficiency in reteaching the same material time and time again. Allows us to separate that, put it online, and then the in-class part, right, can be much more interactive, much more educational, because using that disputation format where we have sort of supervised defense in opposition to theses. So if you're in the class, in class, I'll talk about that much greater depth. So hopefully you're in the class and you'll watch that. So at this point, I'm going to turn off or end the part A. And when we come back, we'll talk about sort of some stories from ancient Greece until the scientific revolution and ending up with Newton, about how the model that we used in the first half of the class, at least, that elliptic orbit model, was developed. So hopefully it'll give you a suitable impression of that. So I'm just going to stop now, and I'll see you again in part B.